Good morning, students. Welcome back to the final video lesson from the topic of thermodynamics. Today we shall study about Carnot's theorem and principle of a refrigerator. So in a previous class we had discussed in detail about the working of Carnot's heat engine. We had seen how the Carnot's heat engine undergoes several processes, a reversible process, and once taken through a complete cycle, what is its efficiency? So based upon the formula of efficiency, we had drawn some important conclusions. So that particular conclusion is encapsulated in Carnot's theorem. It states that no engine working between two temperatures can be more efficient than a Carnot's reversible engine working between the same two temperatures. That is, no heat engine operating between the given temperatures, two temperatures, can have efficiency greater than that of a Carnot engine. In other words, it means that all the engines operating between a given constant temperature source and a given constant temperature sink, none has a higher efficiency than a reversible engine. In case we assume that one engine is more efficient than the other, both working between same two temperatures, then it can be proved that this assumption leads to the result that heat can be conveyed from a sink, that is a body at lower temperature, to a source, that is a body at higher temperature, without performing any work on the working substance. Now that is against the second law of thermodynamics. Hence, the reversible engines working between the same two temperatures cannot have unequal efficiencies, and hence it proves the Carnot's theorem. Let us study about the principle of a refrigerator. What is a refrigerator? A refrigerator can be looked as a Carnot heat engine working in reverse direction. Thus, when a Carnot engine works in opposite direction as a refrigerator, it will absorb an amount of heat Q2 from the sink, that is the contents of the refrigerator, at lower temperature T2. As heat is to be removed from the sink at lower temperature, an amount of work equal to Q1 minus Q2 is performed by the compressor of the refrigerator to remove heat from sink and to reject the total heat Q1 to the source, that is the atmosphere, through the radiator that is fixed at its back. So this is how a refrigerator works. Now in the figure you can see the block diagram. It is actually the block diagram of a refrigerator in which the same principle has been shown. Let us find out the coefficient of performance of a refrigerator. Now what is coefficient of performance? It is defined as the ratio of the quantity of heat removed per cycle from the contents of the refrigerator to the work done by the external agency to remove it. It is denoted by beta. Thus, we can write down beta to be equal to Q2 by W. So that is equal to Q2 divided by Q1 minus Q2. So let us now derive the expression for the coefficient of performance of a refrigerator in terms of the temperatures of the source and sink. So as beta is equal to Q2 by Q1 minus Q2, so we can write down beta to be equal to 1 by Q1 minus Q2 minus 1. Now for a Carnot cycle, we know Q1 by Q2 is equal to T1 by T2. So we can write down beta to be equal to 1 by T1 by T2 minus 1, or we can write down beta to be equal to T2 by T1 minus T2. Now for a refrigerator, the value of coefficient of performance is always less than the value given by this equation. So it may be pointed that higher the value of beta, more is the efficiency of a refrigerator, and as the refrigerator works, T2 goes on decreasing without causing any practical change in the value of T1, and the value of its coefficient of performance goes on decreasing. So this would be all for today's discussion. Thank you.